Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate the standard change in free energy for a reaction. So there's a couple of ways, at least two, maybe three ways that you can actually calculate the change in free energy, the standard change in free energy of a reaction. In this video, for this problem, I'm going to show you how to use one particular way, and that is to use your change, the standard change in enthalpy, as well as the standard change in entropy to calculate the standard change of free energy of a reaction. So let's get into this. So the equation that I just mentioned is this one right here. So we're going to use delta G, the standard change in free energy, is equal to the standard change in enthalpy of the reaction minus the standard change in entropy multiplied by the temperature. Okay, so the first thing we want to do is make sure our temperature is in Kelvin. So again, you're going to add 273 to this, and that's going to be equal to 298 Kelvin. So there's our temperature in Kelvin. And so now what we're going to do is we're going to calculate separately the delta change, the standard enthalpy change, standard entropy change. And there we're going to use the sum of products minus sum of the reactants. So let's write down the first equation. So here we're going to use delta H, the standard delta H change in enthalpy is equal to the sum of the products. So we're gonna take the moles in our balanced equation. These are the coefficients. So it's going to be the moles of products multiplied by their respective delta H of formation, standard enthalpy of formations for those products. So this will be products. And we're going to subtract that from we're going to subtract the reactants from that. So basically, again, it's going to be the sum of the enthalpies of formation of the reactants multiplied by their respective coefficients. So that's going to be the standard enthalpy change, enthalpy of formation of the products, or I'm sorry, reactants. Reactants. Okay, so we're going to use this equation. So over here, I have a table. This information is going to be coming from tabulated sources. So you're going to have to look this up on a table, in a textbook, internet, whatever is provided by your teacher, professor. But here I have a table of the important information that I need for this reaction. So I have the standard entropies and the standard heats of formation for the products and reactants in the table. So I'm going to use the delta H of formation to put into here. So products first. So we only have one product, that's SO3. And so I'm going to take the coefficient, which is my n here. So that's going to be 1. So this is equal to 1. And I usually put square brackets around it if I'm going to add a bunch of them together. But since I only have one product, I'm not adding really anything together. That's what the sum is referring to. I'm adding all the products together, but I only have one product. So it's going to be 1 coefficient for my SO3 multiplied by its standard heat of formation, which is going to be negative 395.7. And this is kilojoules per mole. So that's negative 395.7 kilojoules per mole. Okay, and that's the only product I have, so I'm not adding, I'm not summing anything together. So I'm going to subtract that out, the sum of my reactants. I have two reactants here, so I'll put a square bracket there. And the first one is SO2, and I got a coefficient of 1, so that's going to be my N. So that's 1, and I'm multiplied by the standard change in the formation, standard enthalpy of formation change. So that's going to be here. So that's a negative 296.8. So a negative 296.8. Again, that's kilojoules per mole. And then I'm going to add to that my next reactant, which is oxygen, and you'll see that that's a 0. So my coefficient here is 1/2, so that would be 1/2. And then the delta H of formation, the standard enthalpy of formation of oxygen, since it's an element in its standard state, that's 0. So thing to remember is that the enthalpies of formation, standard enthalpies of formation for elements or compounds in their standard states is going to be 0. So, or elements in their standard states, I should say. So that's 0, and I close this off with a square bracket. And so now I have everything added to my equation, so now I just calculate this out. So when I calculate this out, right, I'm going to calculate this part, and then subtract. And when I do that, I get a negative, I'll put it here, I get a negative 98.6 kilojoules per mole, or I should say just kilojoules, because the moles canceled out, right? So because this is the number of moles cancel out with moles, so I end up with kilojoules. So here is my delta H. Or no, actually, it doesn't cancel out, I don't think. Yeah. So these are ones, they're moles, but anyway. So that is the delta H. Now I do the same thing with my entropy. So the entropy equation, very similar. So the standard change in entropy for the reaction. So this is reaction. And that's going to be equal to, again, it's very similar, this sum of the products minus the reactants. So the coefficient multiplied by the standard entropy of the products, right? Minus, again, the sum of the standard entropy of the reactants multiplied by their coefficients. So coefficients multiplied by the standard entropy of reactants. So now all I do is I plug in the information from my table into the equation. So here, so again, I have one product, so only one product. So that's going to be equal to, and so that's going to be SO3. So I only have one SO3. So again, 1 times, and then the standard entropy of SO3, 256.8. So 256.8. And this is joules per mole Kelvin. So that's joules per mole Kelvin. And this is gonna be the number of moles, so we'll just get rid of moles here just to be exact. Okay. So then now we have the product, and then we're going to subtract out the reactants. We got, again, two reactants, so we have one SO2. So we're going to put our square bracket here. So 1 times SO2. SO2 is negative 296.8. So negative 296.8. And then, again, that's joules per mole Kelvin, joules per mole Kelvin. And then we're going to add to that oxygen. So it's 1/2 for the coefficient. And in this case, oxygen's standard entropy is not 0, it's 205.2. So that's 205.2. And then again, that's joules per mole Kelvin. And so there we go. Now all we have to do again is do the calculation, calculate this out, calculate this out, and then subtract. Okay, so let's go ahead and do that. So we do that, and when we do that, we get, hold on a second, we get negative 94.0. So we get negative 94.0, and that's going to be joules per Kelvin, because the moles cancel out at 1 mole times moles. That's going to cancel out, and I'm left with joules per Kelvin, which is what I would expect for my S value here. Okay, so now I have my delta S of the reaction, my standard entropy of the reaction. So now I can plug those in here. So I should put these in here. So the standard free energy change of a reaction is equal to the standard enthalpy change of a reaction minus the standard entropy change of reaction multiplied by the temperature. So now I got everything I need. I've got my delta H, my standard enthalpy of the reaction. I got my standard entropy of the reaction. So I plug those two plus the temperature. So now I can calculate delta G, standard delta G of the reaction. That's going to be equal to the delta H of the reaction, which is here. So that's going to be a negative. And by the way, when I do that, you want to make sure you convert kilojoules to joules, because I have joules here. So basically, I'm going to multiply this by 1,000, right? So just to kind of show you, if I do negative 98.6 kilojoules over 1, I'm going to use my conversion factor. So I know that 1 kilojoule is equal to 1,000. I'm going to put the 1 kilojoule on the bottom. The 1,000 joules goes on top. And then kilojoules cancels out. So I multiply this by 1,000, I get joules, right? So that's going to end up being equal to negative 9.86 times 10 to the 4 joules. So that's what I'm going to put here. So I have a negative 9.86 times 10 to the 4 joules. And then I'm going to subtract my delta S reaction times temperature. I have my delta S there, so that's going to be minus a negative 94.0 joules per Kelvin, multiplied by the temperature, which is 298 Kelvin. So now all I have to do is just do the calculation. I'm going to multiply these together. A negative times a negative gives me a positive. So this is going to be positive. This is going to be negative. Let's see what we get. When I add those together, I get, what do I get? I get 7. Oh, hold on a second. I get, what was my calculation? 70,000 or 7.09. 7.09 times 10 to the 4th joules, or if I convert that to kilojoules, that's going to be, oh, I'm sorry, that's negative. I got a negative 7.09, and that's going to be negative 70.9 kilojoules for my standard free energy change for the reaction. So it's negative, so that means that this reaction is spontaneous. So that's it for this video. I hope you enjoyed it. I hope you learned a lot from this, and I hope this makes sense to you now after watching my video. If so, then please like my video, share it with your friends, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell so you can be notified by all my videos. Select all when you do that. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.